Well, hello everyone, and welcome to Prep 8. So almost this entire unit is about this one blue dot right here. And that'll become more apparent as we get into it. So let's first talk about an example, because examples always help. So here's our example. We have this population data. We have profit per sale, location, and vehicle type. And we've got lots of records. Okay, so close to 200 records there. And now what we're going to do is first take some random samples from this population data, because this unit is all about comparing samples with a population. So first we'll take small samples, sample size of 2. So these are random samples pulled from this numeric data over here. And you can see each sample has 2 records, and then we take the mean of those 2 records here. All right, now let's go to the graph so you can see what's going on. So on the graph, the black line here represents the population. So this is actually graphing all of those data points from the population. The red line, on the other hand, represents sample sizes of 2. And these square blocks represent these actual means that you see here, right? So we can actually see how the means distribute. And you can see that they distribute fairly widely. And that's what happens when you have a sample size of 2. All right, now let's talk a little bit about the blue line. So we're going to do the same experiment, but this time we're going to take sample sizes of 30. Again, from this population data over here. So here's sample 1, sample size of 30. There's the mean. Sample 2, sample size of 30. There's the mean, and so forth. Then if we come back to the graph and we plot those, these are the little blue dots over here. And you can see that the blue dots are clustered closer to the center. So what's the center? The center is the mean of the population, which is the black line. So the blue dots cluster closer to the population mean than the red dots do. And this turns out to be enormously important. So in other words, as your sample size increases, the mean of the samples gets closer to the population mean. So let's talk a little bit about what each of these dots actually is. So each of these dots is a sample mean, meaning that I didn't draw it here, but imagine that there's a line that passes right through that little dot on the way to here, and a line that passes through this dot here, basically a curve that would look very similar to the black curve, passing through each of these dots. And the only bit of that line that we're preserving, the only piece of information, is the mean. So this is a distribution of means. Now let's talk about these little dots in here. What are they? Right? Well, the idea here is that if you did this lots of times, we only did, looks like 15 samples of each, but if we did hundreds and hundreds of samples and plotted them, what we would get are all the dots here. So we'd get the red dots in the red distribution down here, and we would get the bluish gray dots that are in this distribution right here. So now let's get into some actual theory over here. And this theory is going to be really important because the multiple choice questions are directly based upon it. So in this assignment, we transitioned from the probability of a single value to the probability of a sample mean. Let's begin by considering things that intuitively make sense. A sample mean will approach the population mean the larger the sample. The mean of an infinite number of sample means will be the population mean. Some will be high, some will be low, but they will average to the true population mean. Number 3, a sample mean is more likely to be closer to the population mean than a randomly chosen value from the population. All right, you can actually see that here, right? If we pick any of the values along the black line, right, some of them will be pretty far away from the population mean, but the sample means, right, even the ones with n equals 2, are all closer to the true population mean here in the middle than some of these black dots that would be way out over here. And here's how it intuitively makes sense. So for example, if I pick a random student in the class and ask their grade, there's a chance that it will be a failing grade, far from the mean. But if I average the grades of 2 random students, there is less chance that the average will be a failing grade. If I up that to 10 random students, there is pretty much no chance that the average grade will be a failing grade. A sample of grade averages tends to approximate the class average, and the bigger the sample, the better. A deviation from the true mean is more probable for an individual value than for a sample average, even if the numerical difference is identical, and that's pretty much just saying the same thing. Number 5, the variance of a sample will be close to the variance of the population, and it gets closer as the sample size increases. In a pinch, you could use the variance of a sample as a stand-in for the variance of the population, and this actually happens in a t-test. So remember a minute ago I said that, wow, if I drew lines, curves through each of these blue dots, they would look just like the black curve because the variance would be the same. That's what this is saying. They would have the same very low flat hump that the black line has. However, you cannot use the mean of the sample as a stand-in for the mean of the population, since almost every statistical test involves comparing the two means. So this is all about means. We are going to be comparing means like crazy. All right, now let's talk about the central limit theorem, which is the basis, actually explains why the blue distribution, right, is skinnier than the red distribution. So the central limit theorem states that as sample size increases, the distribution of sample means will approximate a normal distribution regardless of the shape of the population's original distribution. The sampling distribution of sample means is called SDSM. So we have 2 sampling distributions of sample means. We have an SDM30 for sample sizes of 30, which is the blue one, and an SDSM2, sample sizes of 2, which is the red line. And we put them both on the graph just for comparison purposes. Okay. The mean of the sampling distribution equals the population mean. So you can see this. Everybody's got the same mean, right? The population mean is this black line, right? Which is the same as the mean of the sampling distribution of the sample mean. The sample size is 30, and it's the same as the mean of the sampling distribution of the sample mean, sample size 2. The expected variability, what's called standard error, of the sampling distribution is given by standard error SC equals sigma divided by the square root of n. So basically you take the population standard deviation and you reduce it by dividing it by the sample size, but not just the sample size, by the square root of the sample size. That's why the red curve and the blue curve are pointier than the black curve because of this denominator. And the blue curve is pointier than the red curve because it has a bigger denominator. So the shape of all sampling distributions for a given population is controlled by n. If the bigger the n, right, bigger the sample size, the smaller the standard error, right, because the denominator gets bigger, which leads to a skinnier distribution. The bigger the n, the smaller the standard error. For example, 642, right, which was the population standard deviation here, 642 divided by the square root of 2 gives this standard error, gives the 454. But if we take that same number, 642, and divide by the square root of 30, we get 117. The smaller the standard error, the skinnier the sampling distribution. So n equals 30. 117 is a smaller standard error than 454, and that's why the blue line is skinnier than the red line. The rate at which the standard error reduces as n gets bigger slows down. So the square root of 2 is 1.4, but the square root of 30 is only 5.5, not 21, right? In other words, it's not 30 divided by 2 times 1.4, which is kind of what you would expect. And so it's because of that whole square root thing. So the blue graph is only 4 times skinnier than the red graph. not 15 times skinnier, in spite of the fact that the sample size went up 15 times, right? Because you went from 2 to 30. So this is good news for researchers, since it means that getting larger and larger samples has diminishing returns. A sample size of 30 in many cases is good enough. The sampling distribution curve will be skinnier than the population's curve. So here's the population curve, which is black, and even n equals 2 is skinnier than the black curve. And n equals 30 is skinnier, and if we had an n equals 50, it would be skinnier still. And the reason for that is if you divide sigma by another number, it gets smaller. So sigma divided by square root of n is less than sigma. In other words, the variability of the sampling distribution, which is called standard error, will be less than the variability in the population. For the sampling distribution of sample means, z-scores are computed as the difference between a given sample mean, right, the x value of one of the dots, and the population mean divided by the standard error. So if the standard error is small, then even minor differences between means are going to lead to high z-scores. Now, I started out by saying that the whole purpose of this unit, right, the whole reason we're doing this is because of this blue dot. Now let me explain why I started out by saying that. So what you can see here, we know, let's look at the blue distribution. We know that the standard error is 117 in the blue distribution. What that means is that the distance between this black line and the first blue line is 117. And the distance between this blue line and the next blue line is also 117, right? And yet this dot, right, this dot is way out here in the tail. So in other words, it's more than 2 standard errors away from the mean. And anytime, 2 is like a magic number. Anytime you're more than 2 standard errors away from the mean, chances are that's significant. And so we basically come up with a rule, right? And you'll see this because in future assignments, this little area here will be painted green as the rejection region, and we'll effectively say, hey, if we observe a sample mean of 2154, then we're simply going to make the claim that that's so unlikely given this population that we could end up with a sample mean of 2154, that we're going to say it didn't really come from this population, it must have come from another population. That's the claim that we're going to make. Now in this case, we'd actually be wrong, and that's the downside. You can be wrong. The reason we'd be wrong is because this sample mean actually did come randomly from this population. But notice it's the only one of all the sample means that we took. It's the only one that exceeds 2 standard deviations, or actually I should say 2 standard errors from the sampling distribution. Even in the case of the red, right, none of them exceeded 2 standard errors, right? This one got close, and maybe this one over here got close, but none of them exceeded 2 standard errors because the standard error is bigger on the red distribution. So what we're going to be looking for in all the lessons that follow is we're going to be looking for sample means more than 2 standard errors away, and we'll calculate this, right? I mean, I'm using 2 as a rule of thumb, but we're going to be looking for population means, sample means, sorry, I should say, for sample means that are more than 2 standard errors away. And if we find them, we're actually going to make the inference that, hey, right, that actually means something, and it means that that sample probably did not come from the population. Now, we could be wrong, and we'll acknowledge, every time we do one of these, we'll acknowledge the type of error that we might have made. But we're still going to make the statement and stand by it. Okay, so this is giving you lots of information about central limit theorem, the sampling distribution of sample means, and standard error. And we'll be asking you multiple choice questions about all those terms as the lesson goes on. We'll pick up on the next tab. We're going to or actually on most of the tabs here, we're going to pick up with specific examples. So we'll see you soon.